Hey everybody, welcome back. So what we're going to do now is we're going to look at a specific aperture, the single slit, and we'll see what the diffraction pattern looks like if we send light through this single slit. So you can imagine, as I've shown down here, that we have this opaque piece of material. In other words, a piece of material that light can't get through, but we have this opening, what we call the slit. And for reference, I'm just going to call the width of the slit big D, okay? Because there'll be a formula in the next slide where we use the width of the slit, and we'll call it big D. Okay, so what we're going to do is we're going to come in and we're going to look at one wavelength. So we're going to use a laser because we're going to get a specific pattern for each wavelength of light. So we want to look at just one pattern. So if I come in with my laser beam and I overfill this slit like this, on my viewing screen downstream, I'm going to see a pattern of light like this. Now notice, this laser beam is hitting the vertical sides of this slit. So I'm not hitting these horizontal edges. Okay, so I'm only going to get spreading out in one direction. And you can see that if I'm hitting the vertical sides of this slit, the light spreads out horizontally. Okay, so it spreads out horizontally when it hits these vertical edges. All right, so a couple things to notice. First, the light is definitely spreading out. The intensity, you can see, the peak intensity or brightness is right at the middle of the pattern. And if you draw this reference line, this dashed green line, from the center of the pattern, that goes right to the center of this slit. So that's a nice reference axis. And then the brightness falls off as you go to the right or to the left from the center. But the intensity doesn't decrease uniformly. There's a variation in that brightness. Look, in fact, it forms what almost look like the fringes, right, in the double slit pattern. But we don't call these interference fringes. We call these diffraction peaks. So this is the central diffraction peak, or the CDP. And you see this dark spot. At the center of that dark spot, the intensity is in fact zero. There's a point right here where the brightness or intensity is zero. There's one over here too on the left. And if you measure the distance on the screen from those two, between those two intensity zero centers, that forms what we call the width of the central diffraction peak, the CDP. And what you notice is that if you measure the width of these secondary peaks, so if I go from that point right there, intensity is zero there, and I measure to where the intensity is zero here, I get the width of this peak, and I can get the width of the other secondary peaks. What you notice is that the width of the central diffraction peak is about 2 times the width of the other intensity peaks. Okay, now, can you actually predict this intensity pattern, this diffraction pattern? You can. In fact, that was a big triumph for the people like Young who were trying to say that light should be treated or modeled as a wave. It requires some more complicated wave mathematics. We won't look at that derivation, but you can derive this. Okay, so pretty cool. All right, now, what I'm going to do in the next one is I'm going to do an overhead view. So now imagine you're looking down on the slit. So here's the slit width, D, and the laser beam is going to be clipping these edges, this top edge and this bottom edge. And here's our viewing screen here. The distance between the slit and the viewing screen I'm going to call L. I'm labeling these things with symbols because, again, I'm going to write down a formula. Here comes the laser beam. I'm just representing the laser beam with these rays. And if we look, we'll get a pattern something like this. Okay, so again, because this is a top view, we're clipping these edges with the laser beam, this top edge and bottom edge. The light's going to spread out when viewed on this slide vertically like this. Okay, all right, here's that reference axis I was talking about in the previous slide. So if you want to look at a specific point on your viewing screen, that point will form an angle theta. If you draw a line from that point to the center of the slit, you get an angle theta with the reference axis. And it turns out where the intensity is 0 in the pattern, we'll obey this equation. D sine theta is an integer times the wavelength, okay? You don't have to memorize this formula, but I just wanted to point that out. So in this picture, this would be the m equal 1 intensity minimum right there, and there would be the m equal minus 1 intensity minimum down there, and then m equal 2 up here, m equal minus 2 right there. So you get this predicted. And you can do what's called a small angle approximation, okay? Again, you don't have to worry about that, but what you can show is that the distance between the m equal 1 and m equal minus 1 intensity zeros, that again defines the width of the CDP. You get this formula. This is what I wanted to show you. 2 times the wavelength times this distance L over the width of the slit D. And the reason I wanted to show you that formula is, notice that first, it predicts that if we decrease the wavelength, so if we did this instead of with red light, let's say green light, then the width will decrease. Lambda goes down, so W goes down, which means these intensity points where the intensity is 0 are going to get closer together. So the light's not going to spread out as much, okay, if the wavelength goes down. If we use violet light, the light would not spread out as much either. The amount of diffraction would go down. Okay, so that's the wavelength dependence that you should remember. As wavelength goes down, the spreading out goes down. As wavelength goes up, the spreading out or diffraction goes up. The other thing you can see in this formula is the dependence on the slit width. It's in the denominator, so as this opening gets wider, if D goes up, W goes down. In other words, we don't get as much spreading. But we mentioned that in the previous video, as the aperture opening gets wider, the amount of diffraction goes down. As that opening gets smaller, the amount of diffraction goes up. The amount of spreading goes up. The light spreads out more. And that's predicted in this formula too. So I just wanted to show you that formula. We'll actually use a similar formula in our diffraction lab. Okay, and then what I wanted to do is just show you this picture. Now, I got this from a book. Instead of using big D, they use little a for the opening of their slit, the slit width. It doesn't really matter, because what I wanted to show you was this plot. This plot right here is a plot of the intensity or brightness. So you can think of the horizontal axis as the intensity. So you can see where you get a peak intensity right at the center of the pattern. And then this big peak right here, that represents your central diffraction peak. So what I wanted to show you that because I wanted to note that most of the intensity of the light is contained in that central diffraction peak. And then here are those secondary peaks, okay? Don't worry about this sine theta stuff, but this is just labeling where the intensity zeros are in terms of the angle theta. But again, I just wanted to show you this intensity peak, okay? Oh, and also you can see right on this plot, you can see how the central diffraction peak width is about twice the width of these secondary peaks. And again, that's characteristic of the single slit. Okay, now, I have a video where I'm going to be sending red laser light through a slit, and I'm going to be varying the width of the slit. So you should see the amount of spreading to change as I vary the width of the slit. Another way to say that is you'll see the width of the central diffraction peak change. So let me go ahead and show that video. Oops, and I just realized I don't have my PowerPoint open with my videos, so bear with me. I just need to find, oh, there they are. Okay. Hello. Okay, so it's this video right here. Okay, so you can see right now the camera is showing you that central diffraction peak. That's this blob of light right here. And if you look, you can see secondary peaks there. They're real faint. Now, what I'm going to do as I play the video is I'm varying the slit of the width right there. I am making the slit wider. Let me just pause it. So I made the edges get closer, get farther apart. I made the slit opening wider, and you can see how the width of the central diffraction peak goes down and the amount of spreading is less. The whole pattern is getting compressed, if you will. Okay, so the amount of spreading is decreasing and the width of those bright peaks, they're getting smaller and smaller. So I'm going to play it, and then I'm going to start to, let's see, now I'm narrowing the slit width. Let me just pause it. So now I am making the edges of the slit get closer together. I just have a little knob where I can turn the knob and I can open and close and change the width of my slit. Okay, and I think, is that it? Yes. So that's what I just wanted to show you. Oh, now I'm just zooming out to show you the setup. Yeah, see the laser and the slit are here on the desktop, and the pattern is being displayed on the screen. Okay, that's it. Okay, let's get back to our PowerPoint. I think that's it for this part. Oh, no, it's not. Oh my goodness, I forgot. I wanted to go back and revisit the double slit interference pattern, because now that we've talked about diffraction, we can actually fully understand that double slit pattern that we looked at when we talked about interference. So the way I'm going to do this, it's going to get a little crowded on this slide, but I think this shows exactly what's happening. This top pattern is what would happen if we sent the light through just one slit, right? You see it right there. Okay, you can see the central diffraction peak about twice as wide as the other peaks. But if we now take this laser and shine it through two slits, the width of the slits is going to be the same as the width of this single slit. Okay, but I'm going to be shining the light through two slits. You're going to get this pattern. Okay, now notice, in the single slit, you see that central diffraction peak? Well, look at the double slit pattern. You still see that central diffraction peak right there. You see it? Okay. But you now see those interference fringes formed in that central diffraction peak. You see the fact that you have, look, 1, 2, 3 bright fringes and 1, 2 dark fringes within that central diffraction peak. And similarly here, you can see right here, we're starting, that's an interference fringe that's occurring. See right here, if I go from here to here, that's this diffraction peak, but I'm getting some interference fringes. So you can still see the remnants of the single slit diffraction pattern, but superimposed on top of that, if you will, are those interference fringes that Young analyzed, that we analyzed. Okay, and so it's really a combination of the single slit diffraction and those interference fringes. So that explains the overall pattern. And you can also, I don't know if this will help, you can show this graphically. So there's a lot going on here on this plot. Let's break it down. So first of all, look at this blue curve. See this blue curve? That is the predicted intensity pattern versus, they have it versus angle, okay? But you can also think of this, if you wanted, as position on the screen. It would be a similar plot. Vertical, it's just the intensity, the brightness. So this blue one shows you the single slit diffraction pattern, if you were to plot the intensity of this one. Okay? If you just plotted where the interference bright points and dark points are, if you just plotted the interference pattern, you would get, so in other words, you ignore the spreading, well, the fact that the intensity decreases with diffraction. So if you assume that the light just spread out uniformly with no variation in intensity, you would get this sort of light purple curve. See that? So that's telling you where the centers of the bright fringes are. It would be here, 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 where you have the peaks of that light purple curve. Where the centers of the dark fringes would be if the light was of uniform intensity, right? In other words, it's spread out uniformly is what I mean. The centers of the dark fringes would be here, boom, 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 boom. So if you take the actual mathematical product of this blue diffraction plot and this light purple interference plot where you assume that the light spreads out uniformly, you get the actual intensity plot, which is this red together. So this pattern right here that you see where it says double slit, it's this red intensity pattern. So again, what this plot is trying to show you is that you can think of this as combining the single slit diffraction with Young's analysis of just worrying about where are the centers of the bright fringes and dark fringes. And the overall pattern that you get is actually predicted down here as the product of those two plots. Okay? So this is just a visual way, or I should say a graphical way of explaining the overall, the total pattern that you see when you send light through a double slit. Okay, so again, in summary, the light going through each of the single slits it's diffracting, spreading out, and then you're getting the interference of those two diffracting waves to give you the overall pattern. So I thought I would just show you that. So again, we can fully explain that double slit pattern by looking at both diffraction and interference. Okay, that's it for this video. In the next one, we'll consider what happens when we send light through what we call a circular aperture, a circular hole. Okay, see you in the next one.